recording. Okay. Thank you. Uh, yes, hello everyone. I'm Yan Yang. Today I will present the paper Forest Before Trees, Latent Superposition for Efficient Visual Reasoning by researchers from MBZU AI, Fudan University, Renmin University of China, and Harvard. This work proposes a new way to perform visual reasoning inside vision language models, moving from explicit textual chain of thought to efficient latent space superposition. And here is the outline for today's presentation. I will start by motivating the problem, why existing visual reasoning approaches are limited. Then I will walk through the methodology in detail. After that, I will present the experimental results followed by deeper analysis and discussion. And finally, I will summarize the key contributions. So first part is the introduction and motivation. Let me start with some background. The vision language models, or VLMs, have revolutionized visual understanding by integrating large language models with robust visual encoders. To enable multi-step reasoning in VLMs, researchers have adapted chain of thought prompting from the text domain to VLMs, and the model generates step-by-step textual rationales before arriving at the final answer. However, this raises a fundamental question. Is explicit text really the best medium for visual reasoning? And as we will see, there are critical limitations. So first, while the chain of thought has empowered visual language models with multiple step reasoning, the explicit textual rationales suffer from a fundamental limitation, which is called information bandwidth bottleneck. First, the chain of thought forces continuous visual details like spatial layouts, textual, and subtle rationale cruise through the narrow channel of discrete text tokens, and a huge amount of visual information is irreversibly lost during this tokenization process. And also, this tokenization process forced the model to describe vision perceptions word by word, which is inherently lossy compression. And the rich, continuous nature of visual perception simply cannot be faithfully represented through the sequential text generation. And this raises a question. Can we bypass this bottleneck by reasoning directly in the continuous latent space rather than forcing everything through discrete text? To address this information bandwidth bottleneck, many latent space reasoning methods have emerged. This figure illustrates the key difference using the popular coconut scheme as an example. On the left, on the left is the discrete reasoning. Every intermediate reasoning step is decoded into explicit text tokens through the language model head, and then re-embedded back into the model for the next step. And on the right is the latent reasoning. The hidden states are directly fed back as input to the next step without being decoded into text. And this bypasses the information bandwidth bottleneck, keeping all reasoning in the continuous high-dimensional space. And besides coconut, there are also many other latent reasoning methods, which I will not introduce in detail here. And the advantage of all these approaches is that by staying in the continuous latent space, they bypass the information bandwidth bottleneck. However, there is a critical problem that these methods typically retain the standard autoregressive training objective, which leads to the second bottleneck. Although the latent reasoning method we previously discussed uh, have have retained the uh, uh, good performance. However, they still retain the rigid autoregressive training objective. At each step, the hidden state HT is forced to predict exactly one specific next token C t plus 1. And this means the rich latent representation collapses to a single semantic point before the model has had a chance to grasp the holistic visual context, and it creates a tunnel vision effect where the model commits to local details too early and misses complex visual relationships. And the fundamental issue is the uh, misalignment between the nature of visual reasoning and the training objective. The visual reasoning is inherently uh, hierarchical. Humans perceive the global scene first and then zoom into the local. But autoregressive objectives enforces a strict sequential pointwise mapping that has no notion of this hierarchy. And this is exactly the gap that this paper is designed to fill. Instead of a point-wise prediction, this paper introduced a new training paradigm, allowing the latent state to maintain a, a probabilistic superposition of future possibility before gradually narrowing down. And the key insight behind this paper comes from the uh, Norman's global precedence hypothesis from 1977 in cognitive psychology. This well-established finding shows that the human vision perception inherently prioritizes holistic structure, the forest, before processing detailed components, the trees. And when you look at, for example, when you look at a scene, you first perceive the overall layout and the context before zooming into the individual object and fine details. And this paper applies this principle to VLM reasoning. And the core idea is that an effective reasoning state should not be a pointer to a single future world. Instead, it should be a container of a valid domain of future possibility, and the model should maintain a probabilistic superposition of global features before gradually narrowing down to local details. As shown in this figure in the right, the traditional chain of thought reasoning generates verbal textual rationale step by step, while this paper replaced this with efficient latent superpositions that encode the same reasoning into a compact continuous space, which only contains few tokens. And based on the hypothesis, this paper proposed the laser. The name stands for the latent superposition for effective visual reasoning. And this paper introduces three key innovations. First is the dynamic windowed alignment learning, or DAAL, which replaces the standard pointwise next token prediction with alignment to a dynamic window of future semantics. And instead of predicting one specific next token, the model learns to align its latent state with the entire remaining reasoning path. And the second is the self-refined superposition, which uses the model's unlogic estimates to construct stable soft logic targets. And importantly, this requires no external supervision or teacher model. And third is the entropy regularized intervention, which acts as an implicit curriculum. When the model is uncertain, it injects hard ground truth guidance, and when the model demonstrates a grasp of the global context, it reverts to the soft superposition target. And the result is that the laser replaces verbal textual rationale with compact latent superposition states, achieving both better accuracy and better efficiency. And next, I will introduce these components in detail. And first, let's first walk through uh, the problem formulation. So the laser formulates the visual reasoning as a two-stage conditional generation. And in the first stage is the latent vision reasoning. The model synthesizes a chain of visual concept C, which equals to the set C1 through the C capital T, where each CT here is an abstract semantic tokens like person or like clothes. And the T is the total number, the capital T is the total number of reasoning steps. And in the second stage is the explicit answer generation. The model produces the final response A, which equals to the set A1 through the AM, where M is the number of answer token. And now let me explain the notation of the latent reasoning trajectory. Here, the hidden state HT donate the hidden state at step T, and it is computed by the model M theta conditioned on the image I and the query Q, and all the preceding concepts C less than T. And the hidden state HT is then projected onto the vocabulary space via a linear head W to obtain the logit vector ZT. And a softmax over ZT is applied, which gives the next token probability distribution P theta of CT plus 1 given image I and query Q. And for the standard autoregressive objective, it normally minimizes the cross entropy loss LR between this distribution P theta and the one hot ground truth of the next token, while the laser reformulate this by instead of minimizing the pointwise prediction error for a single next token C T plus 1, the goal becomes maximizing the windowed semantic alignment between the latent trajectory edge and the reasoning chain C. And a crucial component of laser is the training data. The authors need a dataset that captures the intermediate visual reasoning steps, but without expensive human annotation like bounding box. So their approach is to use the GPT-4o as a visual cognitive engine to synthesize the reasoning path. And the key design principle is grounded into the global precedence hypothesis. The synthesized sequence must follow a strict global to local scanning logic. Each reasoning chain starts with a global anchor. The broadest visual context like the kitchen, the place, or the blue sky, the background, and then it moves to the subject localization, identifying the main subject relevant to the question. And next come to the visual evidence, listing visible attributes, actions, and spatial relationships. And finally is the critical resolution, the specific concept that answer the query, which must appear at the end uh, of the text. And after filtering, the author obtained the dataset of 270K high quality samples drawn from 6 visual domains, and the average reasoning node per sample is around 7. And now let me explain the core mechanism, the dynamic window alignment learning, the DWAL. Uh, at each reasoning step T, instead of forcing the hidden state to predict exactly the next token, laser defines a dynamic semantic window WT that encompasses all remaining tokens from position T to the end of the chain, capital T. And in short, this is the set of all future visible concepts after the token at position K. And the critical property is that the window naturally shrinks as the reasoning progresses. As the first step, W1, the window will cover the entire reasoning chain. So the hidden state will encode the global holistic semantics. And as the T increase, the window will shrink like the W3, and the hidden state gradually narrows to more local and precise information. And at the final step, like W5, the window contains just one token, enforcing the exact prediction. And this progressive transition from global exploration to local precision directly mirrored the general to specific nature of human visual processing. And the next is, how does this method supervise alignment with this dynamic window without external soft labels? And in this paper, they introduced the self-refined superposition. The idea is simple. They use the model's own logic to um, as the supervision signal. Specifically, they extract the logic's corresponds to the tokens in the current window WT. And apply a stop gradient operation to detach them from the computation graph, and then compute the temperature scale softmax over just these tokens to get the reference superposition distribution QT. And the stop gradient here is critical because without it, the model would enter an unstable self-reinforcement loop where it chases its own prediction. And the temperature tau controls the sharpness of this distribution. And this formulation encouraged the hidden state HT to maintain a probabilistic superposition of all future visual concepts in the uh, uh, in the thinking process. And I draw this diagram to further illustrate how the self-refined superposition work. So first, on the left side, the hidden state HT is projected through the language model head W to produce the full vocabulary logic ZT. And among these logics, only those corresponding to tokens in the dynamic window WT, which is the CT through the C capital T, are relevant. And these window logics are then extracted and detached from the computation graph via a stop gradient operation, shown by the red dashed array. And the detached logics, denoted as the Z hat T, are shown in the upper right bar here. And finally, a temperature scaled softmax is applied over these detached logics to produce the QT, the reference superposition distribution as shown in this bar plot. And each bar here represents the probability mass aligned to a future token in the window. And this distribution serves as a soft supervision target. It encourages the hidden state to maintain a probabilistic superposition over the entire valid window, and rather than collapsing to a single next token prediction. And this process is entirely self-supervised, and the model uses its own logics estimate as the target, requiring no external teachers or annotations. However, there is a risk relying solely on the soft targets, meaning the model could converge to a high entropy uniform distribution that covers everything but focus on nothing. So this is why this paper introduced the next mechanism to prevent the optimization from diverging into meaningless high entropy distribution. They introduced the entropy regularization intervention. The idea is to dynamically switch between the soft superposition target and a hard next token alignment based on the model's current uncertainty. First, they calculate the normalized entropy of the reference distribution Qt, which indicate how uncertain the model is. And then they construct a hybrid target. If the normalized entropy exceed a threshold eta, they mix it with a hard one-hot target, y hard, uh, for the immediate next token. And if the entropy is below this threshold, and they will use purely the soft superposition target. And this creates an implicit curriculum when the model is highly uncertain and its latent state is unfocused. The hard target provides precise grounding to correct the reasoning trajectory. And when the model has already grasped the global context and shows low uncertainty, the soft superposition target allows flexible and holistic reasoning. And in practice, they set the eta equals to 0.6 so that only about 10% of the tokens trigger the hard intervention, which means roughly 1 in 10 tokens gets a corrective signal, which is enough to keep the model grounded without disrupting the semantic flow. And the total optimizing objective unifies the latent reasoning process and the explicit answer generation. First, the DWAL loss minimizes the cross entropy between the hybrid target P target and the model's predicted distribution P theta. And this aligns the latent trajectory with the dynamic semantic window. And for the answer generation phase, the standard cross-entropy loss is used conditioned on the image query and the completed visual reasoning chain. And the final training objective is simply the sum of these two losses. And this figure from the paper summarizes the complete laser pipeline. On the left, the multimodality input, the image and the query enters the model, and the model then generates a sequence of latent hidden states from H1 to HT, and at each step, a dynamic validity window is defined over the future semantic token to construct a reference superposition distribution. And the early states have a full window covering the entire reasoning chain, encoding the broad global semantics. And the later states have a narrower window covering only the processed visual semantics. And as the reasoning progresses, the window shrinks and the state becomes increasingly focused and precise. And all these window states are optimized via the DWAL loss shown here. And after the final reasoning step, which reach the special end token, and the the model will oh sorry, the training will switch uh, from the visual reasoning to explicit answer generation, where the model will produce the final response token supervised by the standard cross-entropy law. And the entire visual reasoning happens in the continuous latent space. No verbal text generation is needed during the reasoning phase, and only the final answer is generated as explicit text. And next is the experimental result. For the experiments, they used the Cuban 2.5 VL 7 billion instruct as the backbone model, and to preserve the pre-trained visual representation and ensure training efficiency, the vision tower and the modality merger are freeze, and only the LLM parameters are optimized. And the training takes only 320 steps. And the key and the key parameters are the temperature tau are set to 1, and the entropy threshold eta are set to 0.6, and the intervention intensity alpha are set to 0.8. And they evaluate on 6 benchmarks: the B link and the MMVP for visual perception, the MM star for visual reasoning, the HR bench 4K image is for high resolution 4K image understanding, and the hallucination bench for measuring the visual hallucinations, and the Seed Beach 2 Plus for text-rich visual understanding like chats, maps, and web pages. And here, this table shows the main result. This paper mainly compares their proposed laser model against 3 categories baselines: the zero-shot VLMs like GPT-4o and the baseline model, and the tool used and the reinforcement learning enhanced reasoning model like the Vision R1 and the VR rethinker, and the latent reasoning model like MONAD and LVR. And uh, and the laser achieves if we look at the latent reasoning part, the laser model they propose achieves a plus 5% gain in overall score over MONAD, and which is the previous best latent method. And the most improvements are on the hallucination bench and BL link with hallucination and yes, and BL link. And the authors attributes these gains to the dynamic windowed alignment by maintaining a semantic superposition rather than collapsing to a rigid token prematurely. Laser effectively mitigate hallucinations and capture fine-grained visual details. And the laser even suppress the heavyweight RL-based and the tool-augmented method in this panel. Despite this method may operating purely this method may involving the use of tools, and the proposed laser operates purely in the compact latent space without external tools or reinforcement learning. And beyond the accuracy, the paper also claimed they achieves a significant efficiency improvement. This table compare the average number of inference tokens generated by different models, and the baseline Cuban model generates 223 tokens on BR link benchmark, and the explicit reasoning method like the VR rethinker also generate 200 average tokens, and it even used 143 tokens in the HR bench benchmark, which increased the token consumption by 157%. And even the previous SOTA latent reasoning model, which is designed uh, as a latent reasoning framework, still use 118 tokens on BR-link benchmark. And its visual thoughts still occupy a dense latent sequence. While laser achieved its exceptional efficiency, just 6 tokens on B-linked benchmark, and with a 97% reduction and 5.7 tokens on the HR benchmark. This is even better than the LVR, which uses 8 tokens, which is in the B-linked benchmark. But crucially, compared with the LVR, unlike LVR, which suffered from the semantic degradation due to its strict reconstruction objective, the proposed laser model's superposition mechanism encodes richer and non-collapsed semantics information within this compact budget. So the laser delivers the reasoning path of chain of thought models while maintaining the inferior speed of direct answer models, making it suitable for real-time applications. And next is the analysis and the further discussion. So the paper further discussed which specific task categories the laser excel at. The radar chart here on the right shows a fine-grained analysis across 14 distinct task categories, where the laser outperforms baselines in 11 of them. The strengths are expected from the forest before tree design. The laser will excels at visual similarity because the probabilistic superposition allows it to soft match ambiguous visual patterns. And it also excels at spatial relations, grasping relative 3D geometries through holistic scene understanding. And in addition, it shows strong gains in multi-view reasoning, relative depth and counting, and etc. And on the other hand, there are minor trade-offs in 3 categories. The first is the object localization, and jigsaw and the functional correspondence. This task requires precise pixel-level grounding or exact low-level feature matching, like the tree-level task. Since the laser prioritizes the semantic flow of reasoning over rigid pixel reconstruction, and since the training uses only weakly supervised data without bounding box annotations, this trade-off is expected and actually validate the forest first design philosophy. And the model is semantically precise but metrically approximate, much like the human cognition. And another question is, there is a common concern regarding the forgetting issue. Does specializing the model for latent reasoning degrade its general capabilities? And this table shows that the answer is no. The laser is evaluated on out of distribution domains that were not part of the training data. And we can see across all 6 domains, there is either improvement or maintenance of performance compared to the baseline model. And the most impressive gains are on web understanding and on chat comprehension. And the geometry stays the same as the base model, which indicates the spatial capabilities are fully preserved. And the math improves by around 1%, and the relative depth by also around 0.8%. This suggests that the forest before tree hierarchy actually reinforced the model's grasp of global structure, and the learned deductive pattern successfully transferred to unseen logic domain. And the model has not just memorized the training distribution, and it has actually learned a better way to reason visually. And an advantage of laser is its inherent interpretability, which is unique among latent reasoning method. Because laser maintains a rigorous alignment between the visual projector and the LLM's semantic space, so the hidden states can be directly project onto the vocabulary via the frozen language model head. And this means that we can inspect the top K tokens at each intermediate step, which effectively visualizing the model's cognitive trajectory. And the figure here shows an example from the MM-star benchmark where the model must locate the seated person in the image. Well, this image has a silent picture in the foreground. And at step 0, the decoded tokens are lit by SE, which indicates word like sees, and spec, which indicate the word spectator and the crowd. And this shows the model successfully overcome the visual silencing bias and shift its attention to the background audience. And at step 1, the latent state involves to encode the spatial constraints like the fence behind and out. These tokens emerge to define the boundary between the spectator and the background. And finally, at the step 2, this spatial reasoning converges into the semantic decision with probability mass shift to outside and the correct answer C. And this trajectory confirms that the laser performs explicit like multi-hoop reasoning from the entity localization, spatial analysis to the final detection, which entirely were within the compact latent space. And this paper also did ablation study, which isolate two key components. First, they removed the DWAL objective entirely and revert the model to standard next token prediction and model, which leads to significant drops on fine-grained perception benchmarks. And this empirically validates that the probabilistic superposition is crucial for preventing premature semantic collapse. And second, they use a fixed validity window instead of the dynamic shrinking window. And the result shows that this impiles the performance on complex reasoning tasks with less impact on pure perception. And this confirms that the progressive shrinking is essential for enforcing the forest before tree hierarchy, which capture the global context before focusing on the local details. And this figure shows the consistent performance gap across all 6 benchmarks in the ablation study. And the authors also carefully analyzed the entropy threshold eta. When the eta equals to 0.6, about 10% of tokens trigger the hard intervention, which provide the optimal balance. And the number lower to 0.5 raises the trigger ratio to around 18%, which over-constrain the model and hurt the reasoning having benchmarks like the MM-star and the hallucination bench. And when we raise the eta to 1, it means essentially no intervention at all, and the model will fail to correct visual grounding errors and lead to suboptimal results on fine-grained perception tasks. And this paper also, although reinforcement learning is not the main focus of this paper, but they also explored the reinforcement learning extension called the EPG GRPO, where the EPG stands for the expected policy gradient. This framework aligns the training behavior with inference dynamics and enable an autonomous early exit mechanism. The model learns when to stop reasoning on its own rather than always using a fixed number of steps. And the results show that the reinforcement learning enhanced model reduced the even reduced the average token count by approximately 50% uh, on top of already efficient laser, from 6 to 3.4 token on B-Link benchmark and from 5.7 to 2.9 on HR benchmark. And crucially, this efficiency gain comes with no accuracy loss. In fact, the overall performance slightly improves, and the model has effectively learned that concise reasoning paths are often sufficient and it can autonomously terminate when confident. And the framework uses a composition reward combining the accuracy and format fidelity, which is normally used in GRPO, and also an efficiency bonus that rewards early correct termination and a diversity penalty that discourages redundant consecutive hidden states. And here I show a case study from the MM-STAR benchmark. This figure shows how the laser approached the visual reasoning problem. You can see the input image here and the question here. The laser reasons entirely in the latent space, producing only 5 latent tokens before arriving at the correct answer. And the decoded latent token at each step shows that the model follows a structured reasoning path from global scene like the sun forest to the focus evidence and then to the final answer. And this demonstrates both the efficiency advantage and the reasoning quality of the laser's approach. And the second case study demonstrates the laser's capability in multi-image reasoning scenario. The task requires the model to reason across multiple images simultaneously. And this is challenging setting for the visual reasoning. And again, we see the laser's latent reasoning approach handles this efficiently. The model processes all images through its latent space, maintaining a superposition of relevant visual features from each image before converge to the correct answer. And the decoded latent tokens reveal that the model successfully integrates information across multiple images in a structured and hierarchical manner. And this case also validates that the laser's dynamic window alignment learning generalized beyond single image tasks to complex multi-image reasoning, maintaining both accuracy and the efficiency gain we discussed earlier. And here is the conclusion. Here in this paper, they propose the laser, which introduces a paradigm shift in visual reasoning for visual language models. Instead of generating explicit textual chain of thought rationales, laser reasons in continuous latent superposition state. And the 3 key contributions are the first, the DWAL, the dynamic windowed alignment learning, which reformulate the visual reduction by aligning hidden states with a dynamic window of future semantics, preventing the premature semantic collapse through a forest before tree cognitive hierarchy. And second, the self-refined superposition and entropy regularized intervention framework, which stabilizes the latent learning without requiring external annotations. And it creates an implicit curriculum that balances exploration and grounding. And third is an efficiency performance trade-off. The laser achieves state-of-the-art result among latent reasoning method with plus 5% over MONAD while reducing the inference tokens by over 97%. And it demonstrates robust generalization to out-of distribution. domains and stands as the first interpretable latent reasoning approach, which means you can actually decode and inspect what the model is thinking at each step. And the broader vision here is that moving beyond the rigid tokenization, Forrester's effective multimodality latent reasoning. And they also released their code to the GitHub. And that's all for my presentation today. And I'm welcome to your questions.
Thank you, Yanting.